All right. Okay, so welcome everybody to the second session. Thanks for coming. So I'll just very briefly just say, so my name is Nathan Clisby. I'll be chairing the session. I just want to quickly say that to me, Richard was not only a person of genuine decency, he was also an inspiration to me for leading a relentlessly creative and interesting life. And I'm very sad that we've lost someone who's such a wonderful person. But now I'm going to hand over to Gary, who's going to give the first talk of this session. And so take it away, Gary.
Thank you, Nathan. It's been wonderful. So what I hope to tell you about today is really work that started sometime in 2009 when I was doing my postdoc at the University of Melbourne. Richard was the person I interacted with most closely, I would say, in Melbourne. And so a lot of the work that I'm going to talk about today really started over that 2.5-year period that I interacted with Richard. Recently, over the past kind of 2.5 weeks, I've been digging through a problem that I'd like to present and came across this old problem that I've now just really started unraveling and seeing the depth of it. And hopefully I'll finish off with some open questions and maybe get your input. Many of you are far more expert at this sort of thing, as we've already seen in the earlier session. So what I want to tell you about, we've already seen some of this so far today. So I call this the polymer zoo. What we've seen is that we can study polymers in a variety of different kind of environments by first picking a polymer model, something that we're going to model the actual physical polymer with. In the case of this problem, I'll be using directed walk models, but we've already seen self-avoiding walks, prudent walks, spiral walks, all sorts of possibilities are out there. And then we're going to put this walk model in just a variety of different environments. So in some cases, we study polymer adsorption, which is a polymer interacting with an impenetrable surface here, and the red dots interact these contacts. This was what Bucks and Stu were talking about. Today, I'm going to talk about this localization problem, which you can basically think of as a polymer interacting with two immiscible solvents. So you may think of the oil and water. I'll just call them alpha and beta. And it's important to note here that because these solvents are immiscible, there is a penetrable surface now running between them. So there is some sort of a distinguished line here separating these two solvents, and the polymer will be able to interact with that interface as it can interact with the upper phase and the lower phase. And then I think we heard the mention of an earlier problem that Richard studied deeply, also this idea of a polymer collapse, a polymer interacting with itself, and then studying this expanded or collapsed phase. And this is just the edge of what's possible. We can introduce a second surface in the adsorption problem that is a surface above the polymer, in which case you'll get a polymer confined in a slit or a tube. In all of these cases, we can add monomers of different types along the polymer, so that instead of being a homopolymer, we could study a copolymer and ask how it behaves. And again, we've already seen the idea that you could add a force on the end of these polymers and ask what happens if they are in their preferred state, either adsorbed or collapsed or localized. And then what happens if we come in with an external force and pull them out of that preferred phase. Again, for the rest of the talk, I'm going to focus on the idea of polymer localization. And so let me just give you, I guess, the ingredients here. I'm going to have 3 phases. So my upper phase here is my alpha phase. My lower phase is this beta phase, and the interphase is denoted as gamma. And I'm going to do quite a bit of notational abuse here. Alpha, beta, and gamma will be the ways I identify the phases, but it also turns out that there'll be energies for monomers in each phase and so on. You've seen most of this in the presentation of generating functions so far, but let me tell you a little bit about how this is going to work in this talk. So first thing that I'm going to do is I'm going to take my my polymer, and I'm just going to simplify it into a Dick path type model. So it's going to have up steps and down steps. As Mireille pointed out, this should be the easiest of all the models. It's penetrable. There's no half plane. There's no quarter plane. So I'm really stacking the deck here. I'm picking the simplest model I know, Dick paths. I'm picking the simplest environment I know, that is penetrable. And I want to see what's going to happen. And so this factorization game, you've seen a couple of examples already, but this is, for example, just what you would use to solve the half plane problem. So these are Dick paths factorized by length. And I just make a point here. The way that I've done this, or at least the way that this is done in the background, is that I try to keep things implicit in terms of equations as much as I can. And then I eliminate between pairs of equations. You'll see that the point here is I want to keep things, so all of this is done in Maple, and I want to keep Maple away from taking square roots and trying to simplify things along the way. So for example, if you take equation 1 here, it's a factorization of Dick paths, just keeping track of the total number of steps. So here Z is my variable conjugate to steps, and we see that it could either be an empty walk or a walk that goes up and then is completed by a Dick path that returns to the surface and then completes with another Dick path. So that's the motivation behind equation 1. What I want to point out is that using that one simple equation, and just by decorating different features of the walk, I can now obtain a much richer collection of models to study. So in equation 2, for example, I weight contacts with the surface, and I use the variable C here. So that's my decoration, if you want to think of it that way, for anytime the walk hits the surface. And you can read this off as it's either the empty walk, which is this blue, whoops, apologies, go back, gone the wrong way. There we go. I've ruined my surprises. So you can see the empty walk here is this blue. And then if the walk continues, then it must take a step up. So it picks up a factor of, oh, and I'm missing a Z squared. I have a missing coefficient of power of Z here in equation 2. But once the walk steps up, this portion that's between these two red vertices, that's a Dick path with no contact. So that's just what I called D of Z in equation 1. And then once it returns to the surface, it picks up a contact. That's my C term right there. And then it completes in anything that can have contacts and total number of steps Z. So again, what I would end up doing here is just eliminate between equations 1 and 2, the common variable D of Z, and then I would have an equation that determines DH. The things that I will keep track of for the purpose of this talk is things dealing with contacts with this preferred line, but I'm also going to keep track of stiffness in the model. And so the way that stiffness works is that I will associate a decoration S, or a parameter S, anytime the walk has a pair of collinear edges. So if I save the stiffness model for the next slide, I can take this Dick path factorization and I can put it together to come up with a generating function. I'll call it B of A, B, C, and Z. So this is B for a bilateral Dick path. This is something that exists on both sides of that preferred interface. And here's, for example, one such walk. This is a walk that has 7 vertices in the upper phase. Remember, I called that alpha. And so this gets a weight of a to the 7th. Here, a is a combinatorial counting variable, but it can also be thought of as an energy variable e to the alpha. These are these Boltzmann factors for generating functions. In terms of the beta phase, this is the lower phase. You can count that there are 5 vertices in the lower interface, phase, and so I get a b to the 5th, and then 4 times the walk visits the interface here, and I get a c to the 4th. And in terms of energy here, the parameters that I'm going to be working with, once I'm finished with the combinatorial side of things, I'll switch over to these alpha, beta, and gamma parameters. And what ends up happening is, so here's my generating function b of a, b, c, z. Now my factorization has to include both sides of the surface. So there are walks which go up and then come back down, but also walks which go down and then come back up. And so what do I really want you to know about this? What I want you to know is that this generating function b has 3 singularities in the total step variable z. And so there's a very simple singularity, call it z1, which only depends on the a variable, z2, which only depends on the b variable, and z3 is a more complicated singularity, which depends on all 3 counting variables, a, b, and c. Here in this blue bubble, just want to point out that this is a physical model, chemical model. Typically what we study here is the free energy of this model, and that's given by minus the logarithm of whatever the critical value of z is. And so when we want to study when things change, what we want to look at is, well, we want to look at when z1 equals z2, or z2 equals z3, or z1 equals z2. And so setting pairwise these singularities equal to each other basically allows me to solve for a critical curve, beta critical, which will be a function of alpha and gamma, the other 2 parameters. And these are going to be the phase boundaries that I want to look at in this problem. All right, so here is typically what you see for this simple problem. So in this case, again, the polymer is a chemically identical polymer made up of chemically identical monomers. So every single monomer here is identified as A. It's a homopolymer, and it's interacting with these 2 immiscible solvents, alpha and beta, above and below, and then this interface, gamma, which has this energy parameter C. And so what I see here is that if gamma equals 0, this is kind of the simplest case, if you want to think of it this way, this effectively turns off the interface. And so you just have an energy alpha, which you can think of as wanting to pull the polymer into the upper of the 2 solvents. And then a parameter beta, which tends to pull the polymer into the bottom of the 2 solvents. And so you can see that if I set Z1 equals Z2, these are my 2 simple singularities, I just get a line denoted by alpha equals beta. So this is the phase boundary, the boundary between transitioning from the alpha phase, delocalized into the alpha phase, to delocalized into the beta phase. But then if I set Z1 equal to the complicated singularity here, Z3, then I get a boundary here which separates the polymer from being delocalized into the alpha phase. And you can notice that this d alpha phase here is the dominant phase when alpha is very large and consequently beta is small, or less than alpha. And that's the situation where we think of the polymer as just living entirely in upper interface, upper solvent. But you can imagine that if I start at any value of beta, let's say I start at beta equals -1 down here, and I slowly reduce the value of alpha, then eventually there comes a critical value of alpha, somewhere around -0.5, let's say, at which point it becomes beneficial for the polymer to actually try to stay out of the alpha phase. Now the alpha phase is actually penalizing the polymer for being up there. And so the polymer is finding it more beneficial to, or at least configurations of the polymer which have more of their vertices in the interface are penalized less and therefore favored. And that gives me this localized phase where I think of the polymer as spending a lot of time near this impenetrable surface, this penetrable interface. All right, so that was the simple case. That was the case where we turn off the interactions with the interface, C equals 1. So what if I make C very, very large? So what if I make C bigger than 1, or I make gamma positive? And so you can imagine in this case, this is the situation where now the interface is kind of sticky. It wants to, it wants the polymer to visit, or at least it will favorably weight configurations that have many, many vertices in the interface. And so if I switch back between these two slides, so here's C equals 0, and here's C greater than 0, what you notice is that essentially the localized region grew and the delocalized regions, the individual delocalized regions shrank. And so again, we can kind of make sense of this change, because if C is positive, or say if C is greater than 1, then we're positively weighting the configurations that have vertices in the interface. And so it should be easier, the localized region should grow, and I can understand the movement of these phase boundaries in accordance to what my model is doing. So now I'm going to ask, well, what happens if C is less than 1? What happens if I put a penalty on having vertices in the interface? And so not surprisingly, this now shrinks the localized region or increases the delocalized regions. Both D alpha and D beta get larger. I have to skip back 2 slides to get to this. So this is C equals 1. And then, of course, you can see this is C equal to less than 1. We see those delocalized regions grow, and the localized region is kind of pushed further and further into that third quadrant. Okay. All of this is fantastic. But what happens if I add, say, stiffness to this model? So the way that I'm going to include stiffness is by looking at my walk, and anytime my walk has a pair of collinear nearest neighbor steps, so in here it goes down, down, or it goes up, 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 so there's 4 collinear steps. For each pair of collinear steps, I'm going to associate a decoration S. And so in this case, if you count along, there should be 8 different pairs of collinear steps as I go along. And so this is going to give me, this particular walk is going to carry a weight A to the 7th, B to the 5, C to the 4, and then S to the 8. So a lot of maple goes on in the background here. But the key thing is I eventually get a generating function that looks like B. And this time I have energy parameters for the alpha phase, for the beta phase, for the interface. But I also have this S energy parameter, which you can think of as tweaking to either favor or disfavor collinear pairs of edges. Okay. This is kind of the technical part here. You are more than welcome to, I will talk your ear off if you'd like to hear about it. But really the key change in this factorization here is that you have to be very careful about how you do the gluing of the walks at these 2 points. So depending on which direction this bilateral walk comes in with its first step at this glue point, you can either pick up a collinear pair if it happens to go down, but you would pick up no parameter S if it goes up. And then likewise here, if this starts with an up, you want to pick up a parameter S, but if this goes down, then you don't want this. Lots and lots of interesting stuff going on here. I really love this factorization scheme, which actually I think comes from a paper that I did with Richard and Thomas, I think in 2011, where we tried to keep these generating functions expressed as in equations, which we could then pairwise eliminate and not have to solve and get ugly square roots along the way, at least. All right, what do I get? In the up version of these walks, I have the empty walk. In the down version, I have no empty walk, just starts down. And I've run all the different sanity checks I can to make sure that these are actually counting the correct things. And then if I look at the structure, there's still 3 singularities in this model. This time Z1 now depends on both A and S. So you can think of this as determining the free energy in the alpha phase, in the delocalized alpha phase. And so there I need to know how many A contacts I have, or that essentially the walk is entirely in the A phase. And then sometimes I pick up an S and sometimes I don't. That's kind of the nice way to think of this as the 2 different ways of continuing a walk, a Dick path, either up and down, where one of them will be collinear with the previous step and the other one will not be. Likewise, in Z2, I now have a singularity which only depends on B and S. And so this will determine the free energy in the D beta phase. And now I have some big giant quartic in Z squared, which determines the equation for this localized phase. It depends on all 3, actually 4 energy parameters now, A, B, C, and S. I'm going to play the exact same game that I played earlier. I'm going to pairwise set these equal. In fact, I know that Z1 equals Z2 will give me this alpha equals beta line. And I also know that this is symmetric with swapping A and B. And so setting Z2 equals Z3 will give me basically a transpose of Z1 equals Z3. So for the moment, I'm going to try to simplify what you're looking at by only plotting a single phase boundary. That is when I set Z1 equal to Z3. Okay. The other simplification I'll take here is that I'm just going to set C equal to 1. Remember, C being my interface parameter. And we already saw that what happens when you change C is that this entire phase diagram just slides up and down along the alpha equals beta line. So, all right, let's do what I'm going to do. So fixing C equal to 1, I'm going to set Z1 equal to Z3. And here I've just animated this over a range of S values. So this is the regime where S is larger than 1. So this is favoring collinear steps. You can think of this as making the walk more stiff. And so what you see is that, well, as S goes to infinity, here I have S equals 1 for reference is the black curve. So that is what you get if there is no stiffness in the model. This is essentially what we already saw kind of 4 or 5 slides ago. And then as I change S, as I increase S larger and larger and larger, what I see is this phase boundary kind of shifts and slides. And I think this last value here is like S equal to 5. And the exact same thing happens with the Z2 equals Z3. Instead, it slides down. There's a transpose here, something symmetric in the line alpha equals beta. And if I think about what's happening here in terms of physics, this all makes sense. As S gets larger, the delocalized region grows. So this phase boundary moves to the left, and the localized region shrinks. And that tends to make sense because as I make S larger and larger, I'm going to make the polymer tend to go off into the bulk more easily. The polymer will tend to be collinear more often than not, and so it will turn back down towards the interface less often, and therefore spend more of its time in the delocalized states, and thereby be harder to localize. All right, what happens if I make S much, much less than 1? So now if S is less than 1, my steps will be penalized. And as S goes to 0, here you can see there again is S equals 1. That's the case where there is no stiffness. In all these cases, C equals 1. Remember, I've turned off the interface interaction. And as S goes to 0, we see that these boundaries move to the right. And so what happens is that D alpha shrinks in this case, and the localized region grows. And again, that should also make sense because here the polymer will tend to want to turn back towards the interface more easily. So it'll be harder to delocalize and more easy to localize around this interface. Okay. And so that would be the story as far as having a clean story. The rest of what I have to say, and it'll be short, is that this beautiful story is only true if you simplify symbolic in Maple. So after solving all these things, if I run these phase diagram plots and ask it, most of this is done with implicit plot. I'm implicitly plotting some complicated expression of alpha, beta, and C. I get this very nice looking phase boundary. So this is I guess, an exemplar case of C equal to 1. Here, S is less than 1. So everything that I say for the next little bit is for S less than 1. If I do not simplify symbolic, if I just take the expression and plot it, Maple plots this. And so the question is, what is this thing? Is this thing real? Is there some sort of other phase? This is all done by equating the delocalized alpha phase equal to the localized phase, Z1 equals Z3. And so what would I want to track? Well, I thought, first of all, I can determine the value of that critical point, call it alpha critical, beta critical. It's around 1. It's not exactly equal to 1. And so what I decided to do is I decided to consider 2 different beta regimes. I'm going to consider a beta regime here where beta is above beta critical, and then another beta regime where beta is less than beta critical. And what I'm going to do is I'm going to start at alpha equals 0 and basically decrease alpha and ask what happens to the free energy as I walk along this dashed blue line from right to left, and then likewise for this dashed green line. And so, okay, so here, this is the first regime. This is the small values of beta. This is beta larger than beta critical. In this particular case, I fixed beta to be equal to -0.5. And what I've plotted here is alpha. I've plotted the free energy kappa, which is this minus log Z critical, as a function of alpha. And so you have several different lines here. The slant line is the free energy in the delocalized alpha phase. Here, this is kappa 2, the delocalized energy in beta. And then these are these 2 branches that you get from the localized region. And so the dotted point there is precisely where this crossover happens from D alpha to localized. And I can understand that quite well. But then if I pick the value of beta to be very negative, this is all at fixed S value, what I end up seeing is something like this. So now there are these two, again, kappa 3 curves, which are functions of beta. And so they've moved from the previous case. So what is happening here? So these two curves have moved as I change the value of beta, and this far curve has kind of encroached in here, and now is tangential to the D alpha phase. Also there. I'm not sure, this is this third crossover point, this far one at around -0.5, and I'm not sure what that is picking up. But I have lots of animations of these sorts of things in Maple, where I fix the stiffness and vary beta, or fix beta and vary the stiffness. And I still don't quite know what's happening, but that's where things are at right now.
Okay, thanks for an excellent talk. Now, I might have time for one or two quick questions. I'll start with the online participants.
Nathan?
Yep, I can hear you, Stu. Go ahead.
Okay. Gary, have you tried playing the same game with
Yes,
either Motzkin paths or with partially directed walks?
Yes, with both. They both have that extra region. The only difference is that the movement of that original phase boundary in the third quadrant is no longer monotone. So in Dick paths, that moves monotone as I vary S. For Dick paths and for Motzkin paths and partially directed walks, it does not. It actually moves to the right and then back to the left for very small values of S.
So when you're equating two of these singularities, which is effectively what you're doing, you've got a complicated equation there.
Yep.
I mean, could it just be that these other solutions you're picking up are just non-physical solutions of those equations?
So initially I thought that they were either complex things that Maple was just throwing out the imaginary part and plotting. They are not, they are real solutions. I thought it might be something that just oscillates. So it's like a numerical artifact of a solution. It's not, it's a clear crosses from one side to the other. Again, I've kept track of as many different things. So the next thing I'm hoping to do is basically try to calculate the average number of the different energy parameters. So either contacts with alpha, contacts with the interface, or collinear steps.
Thank you.
I think in the interest of time, we might leave it there. So let's thank Gary again for an excellent talk.